Okay, awesome everyone. Hi again. Hope you had a good long weekend. So today's lecture is going to be an exciting lecture. We're going to do Bell's Inequalities and the CHSH game, which, yeah, I really consider the single most profound experimental fact in physics, and quite possibly the most profound experimental fact in science. So yeah, that's cool. We got that to look forward to, but let's first review very quickly what we talked about last time, as usual. So last lecture, we covered the Schrödinger equation. And in particular, we derived the Schrödinger equation just from the fact that we had this postulate that the dynamics were unitary. And then we just took the limit where we evolved the system for a very small amount of time. And that evolution being unitary gave us the Schrödinger equation, I d by dt of psi equals h, acting on psi for some Hermitian operator h. The really non-trivial thing in that equation is the fact that h is Hermitian, and that just corresponds to the fact that the evolution is unitary. Okay. And then the second thing we talked about was how to combine two Hilbert spaces together to make the larger Hilbert space that describes the sort of joint system. And the way we were meant to do that is use the tensor product, which I gave sort of various definitions of. We've got very mathematically fancy, but really the sort of down and dirty easiest one to think about is just that the tensor product Hilbert space of H1 and H2 is just the span has an orthonormal basis labeled by tensor products of M and M, where N and M are orthonormal bases for H1 and H2 respectively. Okay. That's very bad notation, whatever. I just made it up off the top of my head. Should have written down, but yeah, hopefully that is clear to people. And then, yeah, so you just take element of orthonormal basis for H1, element of orthonormal basis for H2, and that gives you an element of orthonormal basis for H1 tensor H2. In particular, the dimension is the product of the two dimensions, which is what we want. Okay, so today, as I said, is going to be Bell's inequalities. It's not actually going to be the original Bell's inequality. It's going to be a slightly more general inequality called CHSH game, which is now commonly called Bell's inequalities, CSSH inequalities, sorry. And in fact, we're going to phrase these inequalities in the form of a game, which is called the CHSH game. Okay. In the textbook, Bell's inequalities is section 4.4 and 4.5. They actually do the original Bell's inequalities. It's actually one of the few books I have seen do that version. So yeah, it won't directly correspond to the stuff doing today, though you can get it as a special case of the stuff we're doing today. But the key point is, yeah, it's the same thing where you're going to get some result that just would not be true in classical physics ever. That is an experimental fact about quantum mechanics. Okay. So we saw last time that there is this state that I called the Bell state that can be written as follows. It's a state in the tensor product of two qubits. It's just a superposition of both states, qubits being in state 0 and both qubits being in state 1, appropriately normalized. And the key point was that this state is not equal to some state phi tensor some state psi for any phi in H1 and psi in H2. Okay, so this is a state on 2 qubits that cannot be described by describing the state on the first qubit and then describing the state on the second qubit. This is a unique thing to quantum mechanics. It never happened classically. So it's often, this state is often called phi plus for reasons that will become clear in a minute. But as I say, it is also known as a Bell state. The state isn't sort of particularly unique. And in fact, there's a natural sort of set of states that all have similar properties that form an orthonormal basis. So we can have what's called phi minus, which is exactly the same state, but with a minus sign rather than a plus. You can check that this is orthogonal to the first state. And similarly, we can have psi plus, which has the 2 qubits be in a different state, so 0 and 1 rather than 0 and 0. And we can have psi minus, which is exactly the same as psi plus, but with a minus sign. So these states form an orthonormal basis for the full Hilbert space of 2 qubits, but none of them can be written as the product of a state on psi 1 and psi, on H1 and H2. So these basis, Bell basis, is called an orthonormal basis of maximally entangled states. Entangled just means that it can't be written as, or at least for the moment, just means it can't be written as the product of a state of on H1 and a state on H2. The maximally entangled part is in reference to the fact that any 1 qubit measurement that I do on, say, the first qubit will always have a 50-50 outcome for any of these states. So in contrast, for example, for a product state that is the product of a state in H1 and state in H2, I could do a measurement on the first qubit in some orthonormal basis that includes the state phi, and then I will get the outcome phi 100% of the time. Okay, so that would be not at all entangled. You can imagine that there's some measurement that, say, gets it 90% of the time, one outcome, but not 100. That would be like partially entangled. But in this case, they're maximally entangled. So any measurement on 1 qubit is 50-50. But measurements on the first qubit, even though they're totally random outcomes, can be correlated with measurements on the second qubit. And we're going to see that in practice. Okay. Okay, so to see that in practice, let's do a measurement on qubit 1 in the 0-1 basis, okay? So we could, for example, do a measurement with measurement operator Z on qubit 1, and then it has to be tensored with the identity on qubit 2 because we want the measurement to just be measuring qubit 1 and not doing anything to qubit 2. Okay, so remember that this Z matrix in the 0-1 basis just looks like 1 minus 1. density identity. In particular, the projectors onto the eigenspaces of this measurement operator, which remember are the things that really determine the measurement, are projector for measurement outcome 1, which is just 0, 0 tensor the identity, and the projector onto outcome of -1, which is 1, 1 tensor the identity. Okay, so now we can check the probabilities, can check that these two add up to the identity very easily, but we can also check the probabilities of getting each outcome. If the state of the 2 qubits is in the Bell state, phi plus, and it's pretty easy to see. If you just, the projector, it's just going to kill the 1, 1 part of this state. And so this is just going to be 1 over square root 2, 0, 0, 1 over square root 2, 0, 0, which is a half. Okay, so that's the probability of getting 1. And so it also has to be equal to the probability of getting -1, just because the probabilities add up to 1. Okay, so when we measure the first qubit, we get a completely random outcome. It's completely 50-50. But now we want to know what happens when we measure the second qubit. So we have to look at what the new state is after we did the first measurement. Okay, the first time we got the outcome 1, then the new state is the original state projected using that projector, which is just the 0, 0 state. So then if we do measurement again, we find that, so this was measure qubit 1. Now we measure qubit 2. In this case, we find that 100% of the time we're going to get 1. And in the opposite case, where we in the first step, we got the answer of -1, then the state after measurement will just be 1, 1. And then we find that measuring the second qubit, we get p -1. We get equal to 1. So 100% of the time, we're going to get the outcome -1. So the key point is that 100% of the time, both outcomes are the same, even though individually, both the outcomes are completely random. Okay, so this is where obviously we get into weird questions about spooky action at a distance and stuff like that. Anyone want to comment on whether they think the results I've just described above mean that if the 2 qubits are separated by, say, a few light years, then there must have been some information traveling faster than the speed of light and breaking relativity and spooky action at a distance and all that stuff? Someone go out of a limb. There are people who argue for both points of view here, so you can't really be wrong necessarily. Come on, someone.
Seems like a game of, oh, go ahead.
No, we're starting the exact same, so you go.
I defer.
Go for it, Sajjan.
Okay. It seems like if 2 people were separated by a few light years, they would indeed know each other's result, but they might not be able to do anything with the information. Maybe they could, I mean, they would still have to communicate classically to tell the other people, the other person, that they know what the other person has. I'm not sure. I haven't thought about this anymore, if there can be something done.
Yep. So that's a great answer. So the first thing to note is that when Bob does his measurement, right? He just gets something that's like 50% of the time he gets 1 and 50% of the time he gets -1. Okay, the fact that that doesn't change depending on whether Alice did a measurement first or not. It's only when you look at the correlation between their two measurements that you see there's sort of non-trivial correlation between the two, and they're not independent random outcomes. So the first thing to note is that you can't use this to like actually send information in practice, but you might still wonder whether that this information has got transferred. It's just not useful information, right? Like the instantaneously the information about Alice's measurement gets shot across the universe. It's just in practice not something Bob can use to learn anything, or the rules prevent Bob from actually learning anything about that information. But that's not necessarily true. At least just when we consider this one measurement outcome, we can imagine scenarios where that hasn't happened. And really the reason for this isn't necessarily problematic is that to create the entanglement in the first place, then we needed to have the two qubits in the same place and interact them, right? Otherwise, there's no way for them to have some dynamics that acts on both of them at once and creates this entangled state. If you don't, that will be more obvious to you by later in the course. So if it's not obvious now, then just trust me. Okay, let's imagine a completely classical scenario that's going to give exactly the same results. What we're going to do is we're going to start by generating a random number it's going to be 1 or -1. Okay? And then we're going to hide a copy of that random number in each of 2 boxes I'm going to have lying around. Okay? Now, I'm going to take 2 boxes and I'm going to separate them by a few light years. Okay. And then Alice is going to open 1 box. She's going to find a 1 or a -1 inside, just written on a piece of paper. It's 50-50 which she gets. Now, 10 seconds later, Bob is going to open his box. What's he going to find? Someone tell me it. Very obvious, but I want to hear one of you say it.
Alice's number.
Great. So he's again going to find 1 or -1, which from his point of view is 50-50. It's totally random. But it's always the same as the number Alice found. And then we would declare, oh my God, relativity is broken. We have spooky action at a distance. Alice did the measurement and then it it instantaneously, without any delay, changed Bob's state from being a random number that was 50-50 of being either to being definitely 1 or definitely -1.
But isn't this like fundamentally different than what's happening in the classical case? Because in this case, we have, there is a number inside the box. We just don't know what it is. Whereas in the quantum case, it's actually some superposition of two states.
Yep. So certainly, the rules of quantum mechanics are pretty obviously non-classical, right? So, it is entirely reasonable to say that this is not the same. But you could imagine that you have some like genuinely stochastic dynamics where genuinely there's like probabilities of being different things. And, until you look, then you just don't, from the point of view of what Alice and Bob knows, then it could be either. It's not a superposition, it's just a probability distribution, but it still could be either in some sense. And then one of them measures, and then suddenly, it's known what it is. It's definitely one. Okay, so as you say, this doesn't look like, in quantum mechanics, it's a superposition instead, which is like a different thing, behaves in different ways. But you might wonder, okay, maybe we like think it's quantum mechanics, and it's like superposition and all this fancy pants stuff, but maybe underneath it all, what's really going on is just exactly this. So we could imagine that there's some ordinary, like classical theory that, we don't know all the details of, and maybe that's even deterministic. Maybe that actually tells you in advance whether it will be 1 or -1. But it's like a statistical theory, right? It depends on a lot of like extra stuff that's going on. It's like thermodynamics or something like that, where it like seems kind of random in practice. And quantum mechanics is just this very good approximation that gets the statistics right? And so when we do these measurements, we they see the same thing, and that's just because there's some classical theory where no action at a distance, nothing weird like that, there's actually underlying it all, okay? So this is sometimes called the idea that there could be a local hidden variables theory. Okay, local meaning that it obeys special relativity, that there's no sort of action in a distance. Stuff over near Alice doesn't instantaneously affect what happens near Bob. Hidden variables means that the idea that quantum mechanics is really just some ordinary classical theory, but with some extra degrees of freedom that we can't see in practice. Those are the hidden variables that tell you what really happens, and then quantum mechanics is just this statistical approximation that pretends to like gives the right probability distributions in practice, but like doesn't know everything that's going on. Okay, so this is sort of what, say, Einstein would have confidently said like has to be the right answer, that you totally believe quantum mechanics works, it gives all these great answers, great, it's like not wrong, it's saying stuff along the right lines, but really underneath there's just some deterministic physics that's completely local and like well behaved and so on. Okay, anyone think that's what happens? Okay, and no one's go out on the limb and advocate for local hidden variables, and that is probably sensible of you, because this question has been definitively answered by experiment, and the answer is no. This is not what happens. This does not mean you actually have spooky action at a distance, but it does mean you don't have a classical theory. A classical theory that just has some extra hidden variables and doesn't have any action at the distance. Okay, you have to give up something. You either have to give up the classicalness or you have to give up locality. And the reason for this is that even though we were able to explain the particular correlation between two measurements that we considered above, in quantum mechanics gives predictions for correlations between all possible measurements in all possible bases. Okay? And any local hidden variable theory would need to be consistent with the quantum mechanics correlations between all possible measurements simultaneously, right? Like you need one model that predicts all the different measurements that could be done. There's a loophole where you can avoid that, which I'll talk about a bit at the end. But basically, that's true. Okay? And turns out that there's a set of inequalities. There's an inequality. There's various other ones you can see, but the nicest one is the Bell inequality. It's an inequality that is satisfied by any local hidden variable theory but isn't satisfied by QM. It's violated by quantum mechanics. Okay. As I say, we're going to think about this inequality in terms of a game called the CHSH game. And in terms of this game, this is a very boring and wouldn't be a fun game to play. It's a very much a classic computer science game, in as much as nobody would ever get any pleasure out of it, but it provides useful insight. And this one provides particularly useful insight. It's the most profound game in the universe in some ways. Because in terms of this game, Bell's inequalities basically says that in any universe, described by a local hidden variable theory, actually I'll just say any universe with local classical physics you can win this game at most 75% of the time. No matter what strategy you use, your probability of winning is always less than 75%. Okay? In our universe, it is an experimentally demonstrated fact you can win about 85% of the time. I really want to emphasize that, yeah, if you don't find the fact that this is like super surprising and uncomfortable fact about the universe, that this is possible to win this much, then I recommend thinking about it more. Like it really, once we've described the game and seen like, why you can't win more than 75% of the time, the fact that like actually in our universe you can should be deeply, deeply uncomfortable. So yeah, really take some time to like think about this and ponder it and so on, because it is very, very weird. But it is an experimental fact. Okay. So here's the game. Let me lay this out for you. And again, I want to emphasize this game is not designed to be fun. It is designed to demonstrate the weirdness of quantum mechanics. Okay. So it's a two-player game. It's a cooperative two-player game between Alice and Bob. Okay. And the way it works is that Alice and Bob get to decide their strategy in advance. Okay, they get to plan out what they're going to do. But then they're going to go off and they're going to go a few light years apart. Or in practice, I think this has been done on like different continents and stuff at this point. I forget the current experimental state of the art, but we certainly haven't sent things a few light years away just to test spell inequalities. But you know, we want to set them further apart so that they just can't send signals to one another. Okay, so they're now isolated in their own rooms. They know some strategy that they planned out together, but then they're going to have to make decisions completely on their own. Okay, and then the tester, me, because I am in charge, is going to send each of Alice and Bob a single bit, okay? A single classical bit. So send Alice a classical bit called A, send Bob a classical bit called B, okay? And these are both, again, just a classical bit, as I said, but they're a random classical bit, right? I'm not getting clever here. I've just chosen these completely random. 50-50 of being either. Okay. And now, yeah, so these go to Alice and to Bob over in their respective rooms. This is time going upwards. They get their message. They maybe think for a bit. They do whatever they like, but just in their own room. And then they're going to send a bit back, okay? Alice is going to send a bit back called X. Bob is going to send a bit back called Y. And they're going to send both of those to me. And I will say, congratulations, you win, if and only if the following condition is satisfied, that little a times little b is equal to x plus y mod 2. I told you it was a very boring game to play. Okay, so that is Alice and Bob's aim, is that they need some clever strategy working together to try and make the sum of the two bits that they sent back be equal to the product of the two bits that they received. Okay, is that clear to everyone? So just to give some very explicit examples, we could imagine that say A equals 0 and B equals 1. Okay, then the product of A and B is equal to 0. Okay, so then if Alice and Bob returned, for example, x equals 1, y equals 1, then x plus y equals 0 mod 2 equals A times B, so they would win. But if Alice returned 1 and Bob returned 0, then they would lose. Okay, that is the entirety of the game. What I want to show is that classically, using any strategy they like, the probability of winning is less than 75%. Okay? I'm going to do this in 2 steps. First, I'm going to assume that their strategy is deterministic. Okay, so they don't do anything random, anything like that. They just plan in advance that if A is such and such, I will return this particular X. If B is such and such, I will return this particular Y. In other words, they choose some functions, F and G, acting on one bit, where X is going to be, if Alice receives A, she will return X equals F of A. And if Bob receives B, he will return Y equals G of B. Okay. Now we want to see whether they can win 100% of the time using a strategy like this. Okay. Suppose that they could. Then they would have to win if A and B are both equal to 0. In that case, A times B is equal to 0. Okay? And X would be equal to F of 0. And Y would be equal to G of 0. So we would have to have that 0 equals F of 0 plus G of 0. That clear to everyone? This is for if they were going to win 100% of the time, this condition would have to be true about those functions F and G. They would also have to win if A was equal to 0 and G was equal to 1. In that case, A times B equals 0. And X plus Y is F of 0 plus G of 1. Okay? So that's the second thing that needs to be true. Third thing that needs to be true is they need to win if A is 1 and B is 0. So we need to have 0 is F of 1 plus G of 0. And finally, they need to win if A is 1 and B is 1. Okay, so in that case, A times B is 1. So 1 has to be equal to F of 1 plus G of 1. Okay. Now, if these equations are all true, then I also get a 2 equation if we add them all up together. Add up all the numbers on the left-hand side, I get 1. What about on the right-hand side? Well, I have 2 times F of 0. I have 2 copies of G of 0. I have 2 copies of F of 1. And I have 2 copies of G of 1. But we're working mod 2, right? So 2 times any number is equal to 0. So all these numbers are equal to 0. So that is equal to 0. So we have 1 equals 0. And we have a contradiction. There is no way to use some deterministic classical strategy to always win this game. Okay. Can anyone tell me what that means about the maximum probability that I can win the game with a deterministic classical strategy?
Well, I guess like the strategy would always have the same outputs for each possible like set of inputs that the person gives, like the game administrator gives. So since you can't win 4 outcomes, you have to win 3 or less.
Awesome. And that, what does that mean about the probability?
It has to be less than or equal to 3 over 4, which is 75%.
Awesome. Great explanation. I can't add to it, so I will just leave that there, right? If we're not winning in all 4 of the different possibilities for A and B, then we must be losing with one of them. It's deterministic, so we would always lose with that case. So we therefore find for a deterministic strategy, winning probability is always less than 75%.
I guess okay. I'm curious, how do we know that it has to be 3, not say 2 or 1?
Oh, it can be 2 or 1. It depends on the strategy. That's why this is less than or equal, right? It's just that if we know that all 4 conditions aren't satisfied, then at least one of the conditions is not satisfied. That means you must lose at least 25% of the time.
So the proposition is there exists at least one way to win 3 times, and therefore.
Yeah, that's a good
okay.
question. That's worth doing. Let me give you a strategy that wins 3 out of 4 times. Let f of A equal g of B equal 0. Okay, so x and y, they just always return 0. Okay, then you win unless A and B are both equal to 1. Right, that's the only case where A times B is not equal to 0. X plus y is always equal to 0. So it's this upper bound is achievable. Okay. Okay, the next step in my classical argument is, okay, sure, for a deterministic strategy you can't do better, but that's just because you couldn't win 100% of the time, and so you had to lose 1 because it was deterministic, right? What about if I do some stochastic strategy where, you know, I do stuff randomly, so sure, sometimes I get 1 wrong, but for every outcome, I at least sometimes get it right. Can this help? Anyone want to say whether this can help or not? Otherwise, I'm happy to give an argument. Okay, everyone's too shy. I'll let you off that one because just had an excellent explanation of the previous bit. So it can't. Here's why. Okay. Any stochastic strategy, say, you know, they plan in advance that when Alice gets her measurement, she's going to like flip a coin, and depending on that coin, she's going to do different things. All the randomness in it, we can move forward and have at the very beginning, right? Like they can just do all their coin flips in advance and then just store the outcomes, and they'll have them ready for when they need to decide on what to do. Okay, so, oops. Oh, come on. Move all randomness the beginning. Okay, and we're gonna just combine all the randomness into one random variable, which I'm gonna call lambda. Okay? Then the probability of winning using this random strategy where we you know, have some random number, or maybe set of random numbers that is labeled by lambda. Maybe we toss 100 coins, right? And lambda captures like which ones are heads and tails. And we do a different strategy depending on which ones were heads and which ones were tails. Then our overall probability of winning is going to be sum over all of the different possible values of lambda, okay, times the probability of winning, given that lambda was equal to lambda naught, times the probability that lambda equals lambda naught. Okay? It's just ordinary rules of conditional probability. Okay? But we said that we moved all the randomness into the random choice of what lambda is, right? So that means this is a deterministic. Given we got some lambda naught, then everything else is deterministic. So for any lambda naught, the winning probability is less than 75%. Right? So the key trick was that we could say the only randomness at the very beginning, just one set of shared randomness that both Alice and Bob use however we want, and then we just condition on the outcome of all that, of what all that shared randomness was, and then yeah, that conditional thing is just a deterministic strategy, says most 75%. And now this overall p-win is just an average over a set of numbers, all of which is less than or equal to 0.75. And so p-win of our stochastic strategy is also less than or equal to 75%. Okay. We've concluded that there is no way to win this game more than 75% of the time. This really should feel like just very fundamentally true, that there's just no way around this whatsoever, right? Like no matter what strategy they use, it's just, they can't do anything. There's nothing that could possibly improve on that. Unless they get very, very clever, and while they're meeting up, they sneakily create a Bell state, and then Alice and Bob head off to their respective, after deciding their strategy, they head off to their respective places, but they each take one of the qubits of the Bell state. Okay, this is the thing that's going to magically let them win more than 75% of the time, and hence is why the Bell state can't just be described. There can't just be some local hidden variables describing what will happen when you do measurements on the Bell state, because then it would just be a classical stochastic strategy, and they would only be able to win 75% of the time. Okay, is that clear to people?
May I ask a question?
Yep.
So what if we do something, a mixture of both strategies? Like if we receive, like for example, in the example that you gave for 75%, you said like if they receive 0 and 0, they're gonna send x and y equal to 0. But if one of them receives 1, then they're just gonna go random. What about?
Yeah. So yeah, what you're saying is they're just going to take a random strategy, right? Like if they get a certain A or B, then they just randomly guess it, right? That's what I'm covering here with a stochastic strategy. That's what I mean by a stochastic strategy, okay? And the point is that they could equally well decide in advance. They could toss the coin to decide which random strategy they're going to use before Alice and Bob separate, right? And then just store the coin outcome. Is that clear?
The same case, because so I'm just saying that if you mix both of these strategies together,
yep.
So like for FA and and GB that you defined for the previous one, you will only set it deterministic if A and B are like 0. If like one of them is 1, you're not gonna.
Yep. But that's still a stochastic strategy, right? It's still like it's a strategy that where if they get A and B equals 0, then they deterministically decide, i.e. their probability of picking certain things is like 1, but it can still be described as a stochastic strategy. So let me write here. So by a stochastic strategy, I mean you have P0 is P of x equals 0 equals some function of A, and P of x equals 1 is 1 minus that function of A. And similarly, P of y equals 0 is some function of B, right? And P of y equals 1 is 1 minus right? That's the strategy you're thinking of?
Yeah, something similar.
Yep. So I can rewrite that strategy by saying that x equals some function of a and lambda, okay, where lambda is like a random variable that may have arbitrarily many possible outcomes that are like probabilistically distributed. And y is g of b and lambda, and those may, they may use the same part of lambda, or they may use a different part of lambda. But any strategy like that I like the one I wrote above can be written as the one I wrote below, okay? But then we see that when you condition on a certain value of lambda, it just becomes a deterministic strategy. And so the overall winning probability using this strategy is just an average over the winning probabilities for different values of lambda. And then, each of those is individually less than 0.75. And so the overall winning probability has to be less than or equal to 0.75. Is that clear?
Yeah, thank you.
Okay, awesome. Okay. So you might say, what changes when Alice and Bob use a Bell state? We just said that like having like randomness and correlation and stuff can't help. The point is that Alice and Bob can choose to measure in a different basis depending on what A and B are. Okay? And unlike just sort of ordinary classical randomness, this can't be like done in advance, right? Because by measuring in one basis, you forever destroy the ability to measure in a different basis. Okay? So they can't just like measure in all possible bases in advance and record the results. It really matters that they keep this Bell state, that they keep it in entangled state until they're separated and receive the messages A and B. Okay. So I'm going to give you a particular strategy that is going to enable them to win 85% of the time. Okay. It's going to be useful to introduce some notation for states, which I'm going to call psi theta. Okay, just means the point on the block sphere with phi equal to 0 and theta equal to theta. So specifically, it's going to mean cos theta over 2 times ket 0 plus sine theta over 2 ket 1. Okay. Going to draw a big block sphere here. Right. Okay. If Alice receives A equal to 1, she's going to do a measurement, okay, that's going to tell her, she's going to do a measurement and that's going to give her X, okay, so she's just going to return her measurement outcome. And the two projectors associated to her measurement are just going to be the computational basis. So if she measures 0, she's going to return X equals 0. And if she measures 1, she's going to return X equals 1. Okay, so this is if A is equal to 1, then if she gets one state, which is the south pole, return X equals 1. And if she gets the 0 state, going to return X equals 0. Okay. Could equivalently write these in this new notation as psi 0 and psi pi. Okay, that's just going to be helpful for doing the calculations quickly at the end. Just means theta equals 0 and pi, respectively. Okay. I'll call this actually PA0. Okay, these are Alice's measurements. If A equals 0, she's going to do a different measurement. A equals 0, she's going to do a measurement in the plus minus basis. So if she gets that the state is in the plus state, then she's going to return 1. This is equal to theta at pi by 2. And if she gets that it's in the minus state, she's going to return 0. Okay, so A equals 0, she's going to do a measurement where we have x equals 1 associated with the plus state and x equals 0 associated with the minus state. Okay, so that was all Alice's strategy. We also need to have Bob's strategy. Bob's going to do something slightly different. If Bob receives b equal to 1, he's going to do a measurement where he's going to return y equals 1 if the state is psi pi by 4. And hence, he'll return y equals 0 if psi is the orthogonal state, which is psi 5 pi by 4. Okay, so Bob's measurement, if he receives b equals 1, is he'll return y equals 1 if it's in this state at 45 degrees here on the block sphere. And he'll return 0 if it's the opposite state. Okay. And finally, b is equal to 0. He's going to do a measure in the last sort of 45 degree basis. He's going to return 1 if psi is 3 pi by 4. And he's going to return 0 if psi is minus pi by 4.
Isn't the first projector you wrote for this case the same as the last one for the previous case? Oh, sorry, those are 5.
No, that would be 7 pi by 4. So these projectors are that he'll return y equals 1 if it's in this direction. This is b equals 0. And he'll return y equals 0 if it's in this direction. Okay. Okay. So the thing to note now, okay, is that if, say, a equals 0 and b equals 0, then the x1 equals 1 state and the y equals 1 state are 45 degrees apart. Okay? If a equals 0 and b equals 1, they're again 45 degrees apart. If a equals 1 and b equals 0, they're again 45 degrees apart. But if a equals 1 and b equals 1, they're 135 degrees apart. In other words, the x equals 1 state is 45 degrees away from the y equals 0 state. Okay? Remember, a equals 1, b equals 1 is the exception where a times b is equal to 1. So that's, yeah, it should seem that should be ringing a bell in your head of, okay, maybe that's why Jeff's making up this crazy strategy. He has some method to his madness. Namely, he got told by someone else how to do it. I don't think I'd be capable of coming up with this trick myself. It's pretty clever. John Bell was a smart man. Okay. But
can I also just, I don't know, like, Is there like a particular reason we're suppressing the phi variable on this? Like typically the theta variable ranges from 0 to pi, but we're kind of letting it do the full circle here.
Yeah, I'm just, it's just convenient to define states that way.
Okay.
Just because all my states are going to be on the, have phi equals either 0 or pi. And I just wanted to use this notation because it makes clear the angle between two states. Okay, that's really the important thing, is the angle in the block sphere between two states, because that's what's going to give the inner product squared. Okay. Okay, so let's, so in principle, we have a whole load of calculations to do to work out the probabilities to eventually work out how often they're going to win using the strategy. Don't worry, once we get the hang of them, it will sort of become obvious how it's all going to work. But let's just start with one very, very explicitly. I'm going to take A equal to 1, and maybe I'll take B equal to 0. It's just going to be a explanatory example. And I'm going to look at the probability that X equals Y equals 0. Okay? Okay. So we're going to calculate this in 2 steps, and then we're going to see that it can be done quicker. So step 1 is we're going to find the probability that just X equals 0. Okay. So this is given by phi plus times the projector into 0 for A equals 1, which is just 0, 0 on the first qubit, tensor the identity on the second qubit, and then we have phi plus. Okay, so basically, as we saw before, this is going to kill off the 1, 1 term, and we have a 1 over square root of 2 normalization factor in each of the bra and the ket, so we're going to get an answer of 1/2. Okay, and then we need to work out P y equals 0, given X equals 0. And now given X equals 0, the state is just 0, 0. And the projector for getting Y equals 0, if B equals 0, is this psi minus pi by 4, right? So we have the identity, tensor minus pi by 4. Okay. What is this? Well, it's just equal to the modulus squared psi minus pi by 4 with 0, which, if we look back at the definition of psi theta, right, the 0 coefficient is just cos theta over 2. So that is just cos squared minus pi by 8, which is equal to pi by 8. Okay. So the overall probability is equal to 1/2 cos squared pi by 8. We did that in 2 steps just to be very, very explicit, but we could have done it quicker just in 1 step by writing that it's just the product of the 2 projectors in the middle. So we would have had 0, 0 from the first qubit, and we would have a psi minus pi by 4 from the second qubit. Okay, it's just because these 2 projectors commute, you can check for yourselves that gives the same answer as the more like stepwise approach above. And again, it is indeed 1/2 cos squared pi by 8. Okay, so because we have like 16 of these to do, it's going to be very helpful to just work out a general formula for what things like this look like, So if we have psi plus, and then we have a projector onto psi theta 1, tensored with some projector onto psi theta 2, phi plus. Okay, so this is just equal to the modulus squared of psi theta 1, psi theta 2, phi plus. So this has two terms. Well, first we have the normalization factor in psi plus, that's 1 over square root 2. So when we square it, we get a half. Then we have the two terms in phi plus, right? First we have 0, 0, inner producted with psi theta 1, psi theta 2. That gives us a cos theta 1, cos theta 2. And then we have the inner product psi theta 1, psi theta 2 with 1, 1. That gives us a sine theta 1, sine theta 2. This is the full formula. Can anyone tell me how this simplifies? Sorry, these are all divided by 2. I apologize. Anyone tell me how this simplifies? This formula should be something you learned as a 15-year-old or something.
Is it like the
doubling
cos of subtraction?
It is indeed. It is indeed a half of cos squared theta 1 minus theta 2 over 2. Okay? So the only thing that matters is the difference between the two angles, theta 1 and theta 2. Okay? Now we have that slightly messy technical calculation in the bag, then everything's going to be relatively simple. Okay? So we can just work out all the different cases. So let's start assuming that they get A and B equal to 0. Okay? Then they win if X and Y are both equal to 0, or X and Y both equal to 1. Okay? What's the probability? X equals Y equals 0. Well, it's the expectation in phi plus of, we have B equals 0 and we're wanting Y equals 0. So that means with the projector is onto psi minus pi by 4. And for Alice, we're wanting A equals 0 and we're wanting X equals 0. And we want, so the projector is onto the minus state, which is psi 3 pi by 2. Right. In particular, the angle between these two things, whoops, is the angle between this blue line and the green line, 45 degrees. Right. So theta 1 minus theta 2 is 45 degrees. A projector onto psi 3 pi by 2 tensor psi minus pi by 4 is just a half cos squared theta 1 minus theta 2 over 2, which is just cos squared pi by 4 divided by 2, half cos squared pi by 8. We're going to see this formula half cos squared pi by 8 show up a lot in the next few minutes. You're going to get very bored of it. Okay, so the other possibility where they win is if X and Y are both equal to 1. When's that? Okay, so we have X equal to A equals 0 and B equals 0. So when I said it was the angle between the blue line and the green line before, I meant it's between the blue line and the yellow line, right? The yellow is B equals 0, the blue is A equals 0. Okay, so again, we're now looking at the one states. So they're the plus state and the psi 3 by 4 state, but again, there's a 45-degree angle between them. So a half cos squared theta 1 minus theta 2 over 2 is a half cos squared pi by 8. So the total probability of winning, just add these up. You win, given A equals B equals 0, is cos squared pi by 8. Okay. A equals 0, B equals 1. Again, they win if X equals Y. So we've got to do the same two cases again. So if A equals 1 and B equals 0, that's the red axis and the yellow axis. Again, the state for X equals 1 and the state for Y equals 1 are 45 degrees apart. So the probability of getting them both is a half cos squared pi by 8. And the X equals 0, Y equals 0 states also give a half cos squared pi by 8. So again, P win is just equal to cos squared pi by 8. A equals 1, B equals 0. Again, A times B is equal to 0. So they win if X plus Y equals 0, i.e. if X equals Y. So let's go back up here. Now we have, sorry, which way around am I at? Sorry, the previous one was the green and the blue, which were 45 degrees apart. Now we have the red and the yellow, which again, the X equals 1 state is 45 degrees from the Y equals 1 state, and the X equals 0 is 45 degrees from the Y equals 0. So again, each of them gives a half cos squared pi by 8. Total probability of winning is equal to cos squared pi by 8. The final case is A equals 1, B equals 1. And now they win. Now A times B equals 1. So they win if X plus Y equals 1, i.e. X is not equal to Y. Okay, so this is the one exception. And as I said before, this is the red axis and the green axis. And here the X equals 1 state is 135 degrees away from the Y equals 1 state. So in fact, the X equals 0 state is 45 degrees away from the Y equals 1 state. So the probability of getting X equals 0, Y equals 1 is again half cos squared pi by 8. And similarly for Y equals 0, X equals 1. So even though it's a different winning condition, we again find exactly the same probability. P win equals cos squared pi by 8. Okay, so what's the overall probability of winning? Someone tell me. If in each of the 4 cases it's cos squared pi by 8, what's it overall? Someone say.
It's cos squared pi by 8.
Great, the average of 4 numbers is equal, average of the same number with itself is equal to that number. I just want you guys to say it. I just want to check that you haven't all completely zoned out because I'm saying too much technical stuff earlier on and confusing you. Okay. Each of the 4 cases, we get this really pretty strong probability of winning, cos squared pi by 8, which I doubt anyone knows off the top of their head. I certainly don't. But it is in fact 2 plus square root 2 over 4, roughly equal to 0.85. Okay. In particular, this is strictly greater than 0.75. Okay, that is completion of the proof that you can beat the CHSH game in our universe with higher probability than should ever be possible in any classical universe. Our universe is fundamentally non-classical. Well, it's either non-classical or it's non-local. I'll talk a bit more about that in a minute. But I'm just going to make one comment now, which is this is This is an optimal strategy within quantum mechanics. You can't do better than this strategy I just showed. Okay.
I have a question. So is this not exactly faster than light communication? Like, aren't they in some way communicating something about their answers to each other as they're playing this game using the spell state?
So that is a great question. Yeah. So that very nicely ties into what I'm going to talk about for the last 4 or 5 minutes, which is what on earth does this all mean? What should we conclude from the fact that we violated this bound? And the answer is that it depends on your interpretation of quantum mechanics. What is true is physics can't just be, we can't just have local classical physics the way like Einstein would have wanted or something. But there's several possibilities for what you could give up on that would let you get around this. And the first thing, which connects to what you were saying and also to what someone said in the chat, is that, okay, so we've ruled out local hidden variables. What about non-local hidden variables? So one of the things that we can give up is we can say, okay, classical physics is still true. There's still some like hidden classical variables that describe the state of the universe. They're just not local. We have faster than light communication. Okay, so the sort of most common interpretation that sort of takes this attitude is what's called pilot wave quantum mechanics or Bohmian quantum mechanics. It's an interpretation. It's not super popular among physicists. It's more popular among philosophers for whatever reason. So the idea is that when you do that measurement, it instantaneously affects the, actually does, you know, send information across the universe and instantaneously affects what's going on at the other point. So that's an option. I personally find it pretty unsatisfying for the following reason, which is, well, A, special relativity seems a very fundamental principle of physics. And B, if you're going to violate it, it seems very weird that you would like violate it, that you actually have information being transmitted, but it's so fundamental that that information can't ever tell you anything useful, right? Like you can prove very rigorously, it's no signaling theorem, that even if you have entanglement or whatever, then you absolutely can't learn anything about what the other person is doing faster than the speed of light. So it would then seem very weird if information was traveling faster than the speed of light, but somehow there's just some rigidly enforced law of physics that means, at least in practice, you can never ever, at least within the framework of quantum mechanics, you can never ever get information out. But it's an option. The other possibility is that you just give up on what's called realism. You give up on the idea that there's some objective state of the universe or whatever. Another example with no locality is what's called objective collapse theories. Should mention that just for completeness, though again, they're not super popular. So no realism, you just say, the only thing quantum mechanics lets you talk about are the measurement outcomes of observers, okay? And the measurement outcomes of observers do not allow information to be transmitted faster than the speed of light. So stop complaining about how this could only be explained by classical physics by, you know, having non-locality, because the universe just isn't classical. It's just not a reasonable question to ask. You can just, quantum mechanics is just a set of rules for the experiences of observers, and that's all you're allowed to talk about. Right, so this, roughly speaking, Copenhagen interpretation, probably still the most popular one. Consistent histories could be thought of as basically Copenhagen, but a bit more sophisticated, sort of more modern updating of Copenhagen. Cubism, quantum Bayesianism, Again, sort of similar in spirit to Copenhagen, but a bit more philosophically precise. It's the third option, which is most beloved of sci-fi, also in some ways, if you ask me, the most literally justified by the maths of quantum mechanics, which is just that measurements don't have a single outcome. And instead, what happens is that you get multiple outcomes being described simultaneously by the same wave function, and that in some sense you end up with multiple copies of the observer measuring different outcomes, and that's how they're able to violate it. So this is the Everett interpretation, or many worlds, which is a bit of a bad name. We'll see later in the course why this is in some ways the sort of literal interpretation of what's going on in quantum mechanics. Yeah, it's also very philosophically radical, right? It says that there isn't a single copy of you, which is pretty crazy. And the final answer, which is possibly the most philosophically radical of all, and most people don't like it, including me, on the grounds that it completely damns your ability to ever do physics, which is that secretly we were making an assumption here, which is that we assumed that the tester, me, was sending values of A and B, which were independent of the local hidden variables describing Alice and Bob's measurement outcomes. So it's sometimes called freedom to choose what basis you measure in, right? But if fundamentally Alice and Bob are quantum mechanical things and they're described by the same universe as everything else, then maybe free will is an illusion, and them thinking that they're choosing what basis to measure in is an illusion. Actually, it's determined in advance what basis they measure in, so that your local hidden variable theory only has to explain like the correlations for one choice of measurement, not all the choices of measurement. And, you know, as we discussed at the beginning, it can do that perfectly well, right? The problem shows up when, you know, it has to be able to explain all possible measurement correlations. So it only has to explain one. It can do it with local hidden variables. This is called superdeterminism. But this is pretty crazy. Sabine Hossenfelder believes in this interpretation. I'm not really aware of anyone else who does. Basically it requires the underlying physics to somehow have a brilliant conspiracy that explains means your choice of what measurement you do, which seems like it depends on all sorts of other things, but is actually completely determined by these hidden variables. I find that completely nonsensical, but other people disagree. No one really knows for sure. There's a question in the chat: is where does entanglement equal wormhole fall into these categories? Good question. I think the answer is it can be made consistent with most of them. I would say that isn't. Yeah, it's certainly. If your entanglement is really, so just so people know, this is a fact in certain theories of quantum gravity that certain entangled black holes are dual to a description where you have a wormhole connecting those two black holes. There's a different description of what's going on where instead of entanglement you have a wormhole. Obviously, if you just have two qubits, you don't really have a wormhole, but you can say maybe you have a very quantum wormhole. Yeah, it's a good question. I think it can be made consistent with any of them. There's a question in the chat as well of, is it possible to test any of these interpretations? No, basically, right? Objective collapse, that is a way of changing quantum mechanics so that you it's what's called spontaneous collapse. And that is testable because it's changing quantum mechanics. But you'd have to do a test on a big enough system that the collapse would be detectable. And generally people have tested, they haven't found any objective collapses, but you know, it could always happen on like larger scales. You can always, like, it's like God of the gaps, you can always push it further up just beyond the bounds of experiment. Otherwise, the whole point of them is that they give the same answers to measurements. So that's the final possible answer, which is the Feynman answer of shut up and calculate. That, like, who cares? Physics is about explaining measurement outcomes. We shouldn't be asking questions about what reality is like, which is to some degree legit, but it's also certainly the philosophical questions are interesting regardless of whether you call them physics or not. Okay, I should let you guys go because it's almost 12:40, so I will stop recording. Thank you very much. See you all on Thursday.